Good morning, students. Let us have a brief recap of whatever we have been discussing in the earlier classes about the negative feedback. I'm showing you on the slide now the general characteristics of negative feedback. So, in the last class, I had shown you the regular formula. The formula of gain for closed loop is nothing but A by 1 plus A beta, where A is the open loop gain. Now, in that equation, ACL equals A by 1 plus A beta. When A beta is much greater than 1, you can ignore that 1 and then ACL simply becomes 1 over beta because AA gets cancelled. So now we can see that with the negative feedback, the gain becomes more stable as the gain becomes independent of HFE of G. Okay. So when ACL becomes 1 over beta, you can see that the term A itself is not there in this particular expression now. That means the closed loop gain becomes independent of open loop gain. Now that open loop gain was dependent on the HFE of the transistor in case of BJT or a GM of the transistor in case of FET. So now the closed loop gain becomes independent of the individual gains of the active devices themselves. So this is a good sign for us. Good sign in the sense the gain is going to become more stable. The closed loop gain is only dependent on the feedback factor now. It is not dependent on the open loop gain. That way, even the device's performance in different frequencies does not matter for us now because the closed loop gain is independent of the open loop gain. This is one great advantage of the negative feedback. Of course, the price we are paying for that is in the reduction of the gain itself. Actually, we wanted that. We wanted the gain to be stable, means we have to have reduced gain. Of course, we also know that in life, when we have to gain something, we will have to lose something else. Everything is not possible always, right? The same thing is there in technology as well. So, if ever we want to have stable gain, then we should forego with the larger gain. That is the idea here. Let me continue. Now, the amount of the nonlinear distortion that was present in open loop gets reduced with the negative feedback. That is because the reduction in gain permits increase in the amplitude of the input signal. See, as the gain is reduced now, actually input signal can be increased because earlier we had a limit for the input signal's amplitude, which means beyond a certain signal amplitude, output would go for distortion or clipping. For example, let us say the input signal is 1 volt and let us say the gain is 10 times of an amplifier and let us say the supply voltage to the amplifier itself is 10 volts. So now gain is 10 times, input is 1 volt, supply voltage is 10 volts. Means the transistor would be operating in the quiescent point where transistor would be exactly at 5 volts when the circuit is switched on. Now when the input signal is given 1 volt, now it is 10 times, so we can get an output of 10 volts peak to peak. Now, if at all we increase the input signal, then naturally the signal will have distortion at the output. Because the maximum supply voltage itself is 10 volts, signal cannot go beyond 10 volts. Naturally, the upper and the lower portions of the signal will be clipped if the input signal is exceeding 1 volt. So, that is called as distortion. Now, when we have this negative feedback, the gain is reduced now. When the gain is reduced, even if the input voltage is increased, there will not be distortion. That is the idea. So, the amount of nonlinear distortion that was present in open loop gets reduced with negative feedback. This is because The reduction in gain permits increase in the amplitude of the input signal for the same amount of nonlinear distortion. So that way, at the output, the distortion gets reduced as the gain also gets reduced. That is the idea. I hope you got this point. Let me see whether I can annotate and let me try to explain. See, we have an amplifier, and let us say to the amplifier, the supply voltage is 10 volts. And let us say the gain is 10 times, A equals 10. Okay, let us say we have an input signal of 1 volt peak to peak. 1 volt peak to peak. Now for this 1 volts peak to peak input signal, we will have an output signal of 10 volts peak to peak. Right? We will have an output signal of 10 volts peak to peak. Because this will be at plus 5 volts. The amplifier will be at the DC level of plus 5 volts. It will go to 0 and it will go to plus 10. This range being off at 5 volts. Okay. Now, if input signal rises a little now 1 volt, let us say it becomes 1.2 volts, gain is fixed at 10, so naturally the signal will rise up. Signal tries to rise up here. Let me raise this. Okay. Now the signal tries to go beyond 10 volts. Here also signal tries to go beyond 0 volts. But it is not possible. It is not possible now. Because it cannot go below 0. It cannot go above 10 volts. So in this particular portion, the signal gets clipped. When the signal gets clipped, we will not have a pure sine wave, or the wave shape of the input will not be retained at the output. The wave shape will suffer distortion. Which means you may give input as sine wave, output you may get as slightly a square wave, or a sawtooth wave also with the output portions clipped. Triangular wave also with the two peaks clipped. Let me show you that. Let me erase this. So let us say, instead of this 1 volt peak to peak, if the input is, imagine 2 volts peak to peak. If the input is 2 volts peak to peak, now naturally you will get an output waveform which is like this. So your input signal is sine wave, whereas output signal becomes somewhat a triangular wave with the upper portion and the lower portion being clipped. Now this is a distortion, which means if you give an input of Lata Mangeshkar's song to an amplifier, at the output you may get Usha Uttup's song. Of course, I am not making fun of Usha Uttup. She is also well talented. But the frequency of Usha Uttup is drastically different from the frequency of Lata Mangeshkar. That way, you give a song at the input, at the output, the amplified song will be distorted. That is the idea here. Now, because of the closed loop gain, let us say because of the closed loop gain, because of the negative feedback, the closed loop gain gets reduced. Now, instead of A equals 10, let us say because of the closed loop gain, A equals now 2. If A equals 2, now you can see here the reduction in gain permits increase in the amplitude of the input signal. Now, the gain becomes lesser. When the gain becomes lesser, input can be up to 5 volts peak to peak now. See, instead of earlier it was only 1 volt peak to peak, now the input can be up to 5 volts peak to peak because 5 into 2 is 10. So the amplitude of the input signal is increased. When the amplitude of the input signal is increased, input signal will not have any distortion, right? So, for the same amount of nonlinear distortion, as the amplitude of the input signal can be increased, the distortion gets reduced at the output. Because at the output, the distortion is going to occur only when the output signal exceeds plus 10 volts, or at the other side, it goes below 0 volts. But that will not happen now when the input signal is increased and when the gain is reduced. That is the idea. I hope you clearly got it now. Now let me proceed further. So one obvious advantage of negative feedback is gain is independent of the device characteristics. Next, one more obvious advantage of the negative feedback is the nonlinear distortion gets reduced with the negative feedback. Now, the third one is due to the lack of dependency on HFE or GM, the noise at the output also gets reduced. See, as the closed loop gain is independent of the device characteristics. In fact, the device generates its own switching noise. There are many types of noises called as transit noise, white noise, avalanche noise, flicker noise. There are many types of noises. You are going to study about noises in more detail in the next year. Not now, because it is a much bigger topic. I am not going to discuss about the electronic noise in detail in our course. But in general, you know that noise is nothing but unwanted signal. Whatever is the input signal, along with that, if another noise is coming, that is unwanted signal. For example, let us say when I am taking class here now, let us say the fan is switched on. Now, along with my voice, the fan's noise also, or the noise that is generated by the fan also is going to be transmitted to you. Now, that is an unwanted noise. Actually, we can say it is a sound. Sound is that is unwanted. Whereas my speech is wanted from your side. That is what I presume, because it is a lecture class. So, along with my speech, if let us say the fan sound is coming, that sound is a noise now, because it was unwanted information, whereas my speech was supposed to be wanted or necessary information. That is the basics of noise in general. At times, noise may be useful, at times, noise may be useless. It depends on how you define noise. For example, let us say you set an alarm to wake up at 4 o'clock in the morning, then even though that is noise, that is useful for you, because you have set up an alarm at 4 o'clock in the morning. But let us say because of that alarm, other family members who are sleeping at your home, they also get awakened. Now they will scold you or they will curse you because they also get awakened, they get irritated. If the alarm sound is much larger in the early morning, it will be audible to neighbors' houses also. So at that time, even neighbors may curse you, or neighbors may start murmuring there, saying that somebody is disturbing their sleep. So how do we define noise? At times noise may be useful, at times noise may be useless, at times noise may be irritating also. Now whatever is the noise we are talking about in the amplifiers, that is actually useless or irritating for us. But in the case of oscillators, the same noise is going to be useful. I am going to tell you about it later on when we discuss oscillators. So the point here is, which one we define as noise depends on our particular context. For example, let us say a mother and a child are playing with each other. When the child is making many crazy noises. The child may not be knowing how to speak properly. Child may be making many crazy noises or many crazy sounds. I should not say noises. It is sounds. When the child is making those sounds, then for the mother, it will be highly soothing. Mother will derive happiness out of the child's crazy sounds. But the same crazy sound may not be causing happiness with other people around the child. There may be strangers around the child. There may be other people around the child. For them, it may feel as if the child is purposefully disturbing them. That is how we define noise basically depends on the context. Now let me come back to the amplifiers. In the amplifiers, if there is noise coming along with the input signal, that noise can be filtered to some extent by making use of filters. You are going to study about filters in detail in the other courses such as digital signal processing or analog communication subjects. In those courses, you are going to study more about the design details of the filters. Again, I cannot discuss all those bigger concepts in this particular course. Anyway, if the noise is present with the information signal, then that can be reduced by means of a filter. But if the noise is generated by the transistor itself, because the transistor will have reverse bias junction, it will have forward bias junction inside. You already know that in case of BJT, base to collector region is reverse biased and the base to emitter region is forward biased when the transistor is operating in the active region. In such a case, the reverse bias junction is there. Across the junction, the charge carriers will move. Now, the forward bias junction is also there. Across that junction also charge carriers will move. Now, the reverse bias junction will have a capacitance. And even the forward bias junction will have a capacitance, because you know that between PN junction there is always a depletion region. In the reverse bias junction, the capacitance is larger because of the expansion of the depletion layer. So, wherever there are junctions, there are these issues. When there are these issues, noises are bound to get produced even inside the device because of the parasitic capacitances, and even the transistor has got a parasitic resistance inside, right? So, due to this, even the transistor may develop different types of noises within, especially at high frequencies. You are going to study about noise anyhow in detail in the future courses. Let me not discuss all that now. But now, let us come to a conclusion that the device is going to generate noise inside. Because basically, inside a device, there are a lot of electrons moving. Whenever there are a lot of electrons moving, electrons will have collisions among themselves, and that is going to cause noise. Now look at this last point, where now the gain is independent of HFE or GM. That means the gain is independent of the device itself. So the noise at the output also gets reduced. Why? Because this noise is proportional to the active device's characteristics. Now when the closed loop gain is independent of the device characteristics itself, naturally noise at the output also gets reduced. This happens because of the reduction in gain as well. Why? Open loop gain was much larger, closed loop gain was much lesser. As the closed loop gain is much lesser, now the amplification of the noise also gets reduced. So naturally, noise will get reduced. To tell you one funny real life example, let us say some person is earning only 5,000 rupees per month as salary or as an income. Now his salary is very less, or income is very less. When the income is, let us say, only 5,000, then his problems also will be very less. Which means he need not pay the bank installment for a car. He need not pay the bank installment for a flat or a house. And he need not buy lot of things every day, or he need not buy going to a shopping mall or going to a big mall like Orion or Mantri Mall or Phoenix Mall. He will not go there at all, right? because his budget does not permit him to go there. And he need not spend lot of money on other things. Now his needs are only the basic necessities of daily food and a place to stay somewhere. That's all, right? So when a person is having income of, let us say, only 5,000 or 10,000, his needs also will be very less. His needs are only for the sake of the survival. Now let us say a person is drawing 50,000 rupees, his income is 50,000, then naturally his needs will increase. He will think of having some other comforts at his life. Apart from the regular food and shelter, he will generate his own other needs. Let us say a person is having an income of, instead of 50,000, let us say it is 5 lakhs. Then when the person is having an income of 5 lakhs per month, naturally he wants to have a lavish lifestyle with a very big flat or a very big house with very big car, sometimes not just one car, maybe 2 cars, maybe 3 cars. Each family members, they want to have their own cars and they want to have a big farmhouse. They will never go to never go through BMTC bus at all. They will never travel with the regular public transport at all. They may never travel in the metro train also. They may always catch flights if at all they have to travel for longer distance. Otherwise, they may always use their own cars. And they may not go to normal restaurants for their breakfast and lunch also. They may always go to 3-star and 5-star restaurants only. So what does it mean? What does it mean is, whenever there is a large amount of income, naturally there will be additional problems. Now when there is a small amount of income, there are only basic problems. Now let me come back from philosophy to technology. Now in the technology, again, when the gain is reduced, everything else is also reduced. All other disturbances also are going to be reduced. Okay. When the gain is increased, all other problems like distortion and noise problems are going to be increased. That is the idea here. For you to understand this concept, I told about that concept. But that concept is also going to be a learning for you. In future, whenever you become very good engineers, remain very good human beings also. Just because you become good engineers, it does not mean that you will have to lose all the human values. Otherwise, generally what happens is, whenever a person's financial income is increased or the money's inflow is increased, naturally people will go for initially money, then later on status and prestige and power. And gradually they become more arrogant, they become more egoistic, they lose their compassion towards the other fellow beings. They don't have compassion towards anybody else as such. They will have only attachment towards their money and status and prestige and ruling power and all such things. Gradually they will lose the divine qualities which are already with the human beings. And someday they will become more arrogant, and at times because of their arrogance only they cause more problems to themselves and to the society. This is what we are observing in the general human lifestyle or in the society. Money is very much required for decent lifestyle. Money has to be earned by everybody and anybody for having a comfortable lifestyle. But earning only the money should not be the goal of life. But so gradually what happens is, people will have only the money, they will lose out all other things. They will lose out the physical health, mental health, even the spiritual health. That is the idea. So let me stop my philosophical advices. Let me come back to the discussion of amplifiers. Let me admit the student who is waiting. Fine. So you can see that when we reduce the gain of an amplifier, we have many other advantages. Gain becomes independent of the device characteristics. So naturally distortion gets reduced and noise gets reduced. Let me proceed. So the advantages of negative feedback. For voltage amplifiers, the advantages of negative feedback can be summarized as higher input impedance, because IS gets reduced due to the negative feedback. When there is a negative feedback, even the current at the signal source also can get reduced, and due to which the input impedance gets increased. Anyhow, we have derived an expression already in the previous class where I had shown you that ZIF equals ZI into 1 plus A beta. Means the closed loop input impedance gets multiplied by a factor of 1 plus A beta to the open loop input impedance. Now, the second advantage is lower output impedance, because when RL increases, V0 does not increase in the same proportion. When the load resistance increases, output voltage does not increase in the same proportion because of the negative feedback, as the gain is now reduced. So, it will result in the lower output impedance. In today's class, we will see how the output impedance is going to be reduced in a mathematical way. So, obvious advantages are higher input impedance and lower output impedance. Okay. The next advantage is stabilized voltage gain, that I have discussed already. And the fourth advantage is increased bandwidth, that also I have discussed already. And the fifth advantage is reduced distortion, that we have discussed in today's class. And the sixth advantage is reduced noise, that also we have discussed in today's class. So these six are the obvious advantages of negative feedback. The only one disadvantage is the reduction in gain. But we are purposefully having a reduction in gain so as to have six advantages. Let me tell you one more real life example. So many people, after a certain age, they involve themselves in a lot of charity. So many rich people also, after a certain age, after they cross a middle age, they involve themselves in a lot of charity. They donate their money to so many other people, or they donate it to so many other organizations, and they want to have more of social contribution. At times, some of these people will take up monkhood also, or renunciation also. At times, these people will take up sannyasa and they will become monks, or they will become saints or adepts, sometimes hermits also, and they will get involved in some other noble activities for social welfare. Why do they do that? They do that because now they don't want any more money in their life. Whatever money they have earned till now, or they have saved till now, or stored, they want it to be utilized for some other means. And when they attain monkhood, even they will stop earning money as well, because they want to be of a larger contribution to the society as such, in the spiritual terms or in the psychological terms, not just in the physical terms. So what does it mean? After a certain age, people will completely stop whatever they have been doing. They will devote themselves into some spiritual penances or spiritual practices or some other type of renunciated lifestyles. The reason is there are much other advantages when compared to the earlier lifestyle. Today I am telling you a lot of philosophical things only. Anyhow, that is how I think. The way in which I think, the same way I speak, because I think in the philosophical manner itself. So that way you can see that even though gain is reduced, there are these six advantages. Same way, for those people, only if the financial income is reduced or the influx of the money is reduced, but they will obviously have many other disadvantages in their life. They will have more of happiness, they will have more of mental health as well as physical health, they will have more of contentment in their life, and they will be having some gratitude towards the gift of life, and they will have better contact with other people who are of the same noble type. So that way, there are many other advantages of even renunciates or monkhoods. Same way, in our amplifier's case, only disadvantage is reduction in gain, but we have other six advantages. Okay. So let me proceed with this now. You have seen these feedback amplifier topologies. You have already seen the series shunt, shunt connections. I have already discussed these things in detail when I discussed that particular textbook page also, when I showed you the pictures, and I showed you such pictures even in the PowerPoint earlier. How do we take voltage as feedback, and how do we connect it as series to the input? That is how at the input you will see series, and the output you will see shunt. So this is now voltage series feedback. Same way this is now current shunt feedback. You can see the series connection at the output and shunt connection at the input. So this is now a current shunt feedback. Similarly, this diagram C is current series feedback, whereas the last one, the D, is now voltage shunt feedback. So it is shunt mentioned here. In the third one, it is called as series. You are already familiar with this picture. Now the characteristics of all the four amplifier types can be improved by the proper application of one of the following four feedback connections. This also we have discussed already. I had discussed about the four amplifier types in the beginning: voltage amplifier, current amplifier, transconductance amplifier, transresistance amplifier. I had discussed those four things. Input is voltage. If output is voltage, that is called voltage amplifier. If input is current, if output is current, then it's called current amplifier. Sometimes it is called as buffer. We will have some applications where we will have to convert voltage into current, and we will have to convert current into voltage. That is when we use the other two types of amplifiers. That way we have four amplifier types. Now in all of those amplifier types, the performance can be improved by means of the additional four feedback connections. Those feedback connections are voltage series, voltage shunt, current series, and current shunt. Okay. In the case of voltage series, the source is voltage, input is voltage, output is voltage, feedback is also voltage. But in the case of voltage shunt, then the source is current. I had shown you why we use a current source there. And input is voltage, output is current, feedback is voltage. Okay. In the case of current series, source is voltage, input is current, output is voltage, and feedback is current. In the case of current shunt, source is current, input is current, output is current, feedback is also current. That way, these are the four types of feedback connections apart from the earlier four types of amplifiers. Series feedback increases input impedance, whereas shunt feedback decreases input impedance. You can observe this. Series feedback is going to increase the input impedance, whereas shunt feedback is going to decrease the input impedance. Voltage feedback is going to decrease the output impedance, whereas current feedback is going to increase the output impedance. Now, whichever line I have word I have shown you in green, that is a definite advantage for us. Whichever word I have shown you in red, that is a definite disadvantage for us as far as the amplifier is concerned. But please recall, sometimes this disadvantage also can become an advantage for us whenever we go for impedance matching. So even the decrease in input impedance can be useful whenever we have to match impedance between two particular circuits. That way, all these feedbacks are going to be useful in one way or the other in different types of applications. So let me proceed now. Now let me continue with the chalk on talk. Instead of the chalk and talk, I am going to stop sharing this particular slide and I am going to start sharing the textbook page. So in today's class, we will see about output impedance. As I had told you last class that let us discuss output impedance in the next class. Now, output impedance with feedback. The output impedance for the connections of that particular figure is dependent on whether voltage or current feedback is used. For voltage feedback, the output impedance is decreased, whereas for current feedback, it increases the output impedance, which we have discussed. We will see it how now. Let us discuss the voltage series feedback, which we had already discussed earlier. Now, the voltage series feedback provides sufficient circuit detail to determine the output impedance with feedback. The output impedance is determined by applying a voltage V, resulting in a current I with Vs shorted out as per the Thevenin's theorem. Now, the voltage V is I into Z0 plus A into Vi. Now, for Vs equals 0, Vi is minus of Vf. When we apply Thevenin's theorem at the input, Vi is equal to minus Vf. Now, the voltage V is I into Z0 minus A into Vf, that is I into Z0 minus A into beta into V. Now, rewriting this equation, we can write it as V plus beta into A into V equals I into Z0. Now, let us find out the output impedance, that is that ZOF, the output impedance with respect to feedback. We get that ZOF is V by I equals Z0 by 1 plus beta into A. So, now you can see the output impedance with feedback is a fraction of open loop output impedance, and at the denominator you will see that 1 plus A beta once again. I have been telling you that we will keep getting this term 1 plus A beta again and again in all the derivations. In whichever way, whichever amplifier, whichever type of feedback we use, always we will keep on getting this particular expression. And actually this particular expression, even though as far as amplifiers are concerned, we are discussing with 1 plus A beta. Whereas next semester you are going to study a course called Control Systems, where the same feedback concept is applied to all other engineering systems in general, not just electronic systems. It can be any electromechanical system also. Even mechanic engineers also study all these concepts as far as their systems are concerned. So, there they always get one equation called 1 plus G into H, where G is the open loop gain and H is the feedback factor. Here we are calling A as the amplifier gain, as beta as the feedback factor, because we are referring this to amplifier. But whenever you get a terminology as 1 plus G into H, then G is the open loop gain of the system as such. It may be an electronic system, it may be a mechanical system, it may be an electromechanical system, it may be an automobile system, it may even be a civil engineering system as such. It is generally applicable to all the engineering systems, where you will have a feedback always for a given system. That way, 1 plus G into H is going to be the term used in general. For an amplifier, we are going to use the term 1 plus beta into A. We keep telling it as 1 plus A beta for our ease of pronunciation. Or it is also easy that we visualize A first, then beta next. A is the amplifier gain, beta is the feedback factor here. Please remember, this beta is not that beta which we have been discussing earlier in the previous modules. In all the three previous modules, whenever we discussed beta, that refer to the current gain of the BJT. Now here beta is the feedback factor of the system or the block. We are discussing the block level amplifier now, not the individual circuit level amplifier. So you can see now that ZOF is Z0 divided by 1 plus beta into A. Whenever A beta is much larger than unity, you can see that the output impedance is a lesser value when compared to open loop output impedance. That way, with the voltage series feedback, input impedance gets increased, output impedance gets reduced by the factor of 1 plus A beta. Let me proceed. Let us come to the current series feedback now. Now, this is the current series feedback connection. The output impedance with current series feedback can be determined by applying a signal V to the output with Vs shorted out. As you know, when we apply Thevenin's theorem, we have to short the voltage sources, resulting in a current I. The ratio of V to I being the output impedance. Figure 14.5 shows a more detailed connections here. You can see this connection. Now, this is a current series feedback. You can see current is taken at the output and it is given in series. And you can see this Zi as the input impedance. and Z naught as the output impedance. Now let us proceed for the expression for output impedance for this particular current series feedback. All these derivations follow the same methodology. The only thing is that you will have to write the block diagrams accordingly. The only way to write is to practice writing again and again. That is the only way. Otherwise, you will get confused. There are 4 feedback connections here, and for all the 4 feedback connections, you will have to arrive at the expression for the closed loop gain, that is AF or ACL. Then you will have to arrive at the input impedance ZIF. You will have to arrive at the output impedance ZOF. Now, unless you write and practice, you will get confused heavily. And it is a definite question in the test and in the exam. Out of these 4 feedback circuits, you will get at least any one of them definitely in the exam. And out of these 3 derivations, you may get all the 3 derivations for the given feedback connection. We may ask you a question, obtain the expression for the closed loop gain for a current series feedback amplifier. Along with that, find out the expression for closed loop input impedance and closed loop output impedance. We may ask out of the 4 feedback connections, any one feedback connection. That is why you will have to practice all these things by writing yourself physically. Otherwise, you will get confused. Because all circuits look somewhat similar, procedure is also somewhat similar. But you should not get confused when you start working on it. Now let me continue. Now the connection to the current series feedback for the output part of a current series feedback connection shown in figure 14.5, the resulting output impedance is determined as follows. With Vs equals 0, Vi equals Vf, same as the earlier case. I equals V by Z naught minus A into Vi. That is V by Z naught minus A into Vf itself. That is V by Z naught minus A into beta into I, because it is now a current series feedback. So Z naught into 1 plus beta into A into I equals V, or ZOF is nothing but V by I. The output impedance with feedback is Z naught into 1 plus beta into A. So here you can see in the current series feedback, output impedance is getting increased by this factor of 1 plus A beta. But even if the increase can help us in future in some applications where we want to have impedance matching between the 2 circuit blocks. So finally, let me come to a summary here. You can see this table. In the table, you can see the 4 feedback connections: voltage series, current series, voltage shunt, current shunt. Now, input impedance is being increased in voltage series. Input impedance is increased in case of current series also. This we had seen in the previous class. But in the voltage shunt, the input impedance is going to be reduced, and even the current shunt connection also going to reduce the input impedance. This we will see later on. Now the output impedance is reduced in case of voltage series, but output impedance is increased in case of current series. Output impedance is reduced in case of voltage shunt. Output impedance is increased in case of current shunt. Now you can see all series connections are going to increase the input impedance. All shunt connections are going to reduce the input impedance. But you can see all the voltage feedback is going to reduce the output impedance. All the current feedback is going to increase the output impedance. Let me annotate to make it clear. See, series connection is going to increase. Series here is going to increase. Shunt connection is going to reduce. See, this is in case of input impedance. Now, let me change the color to show you the output impedance. Now, the output impedance, let us say I'll mark it like this. Voltage is going to reduce, voltage feedback. Current feedback is going to increase the output impedance. Voltage feedback is going to reduce the output impedance. current feedback is going to increase the output impedance. So, my dear students, remember, series feedback is going to increase the input impedance. Shunt feedback is going to decrease the input impedance. So, as far as input impedance is concerned, remember series shunt at the input itself. Now, output impedance is at the output. At the output, you are going to take voltage or current. So, if you take voltage, output impedance is going to reduce. If you take current, output impedance is going to increase. So, always relate whenever it is input impedance, it is input side. Input side we have series and shunt connections. Series is going to increase, shunt is going to reduce. Whenever you think about output impedance, it is at the output side. At the output side, we have voltage and current. And whenever we take voltage, output impedance is going to reduce. Whenever you take current, output impedance is going to increase. Always